This example is an initial value problem because we're asked to find the position of a mass as a function of time. So that means we need to know precisely the position of the mass at any time t. And then also find capital T, the period, and little f, the frequency. They, remember, are just reciprocals of each other. Well, here's the setup of the problem. Just this picture, really. Here's the natural length of the spring. Here is the equilibrium when you attach the weight and it comes down to rest right here. And it stretched at 6 inches. So what does that tell us? From the natural length to the equilibrium based upon this weight, that tells us S. And S, we don't want to say S equals 6, we want it to be in feet, so S is 1/2. And then somebody takes the weight, stretches it down, and the mass is released from rest at this position. So it was equilibrium right here, bring it down to here, and then at time 0, it's just let it go. That's what at rest means. It means you're not applying any extra force, hitting it with a baseball bat or anything like that. You're just letting it go. All right, well, let's see. Recall that we know this equation from a couple of videos, actually. M times, this is dx, d squared x dt squared, the second derivative of x position with respect to time, plus kx is equal to 0, or we could write it like this, and I put a star by that to name that equation. Now, this is a 20-pound weight. We need the mass. We need little m. So 20 is m times g. So m is going to be 20 over g, which remember we do 32 feet per second squared. And that's equal to 5/8. So m is equal to 5/8. Now we need to find out what k is. We need to find out the spring constant. So we can use this. Remember, at equilibrium, this is true. So mg we already know is 20 equals k, and s is 1/2. So k is equal to 40. Okay, since we know what k is, we can look at the star equation. That implies that m is 5/8. Second derivative of x with respect to time is equal to negative kx. And do I want to write that on the other side? I think I do. I'm actually going to use that one. Plus kx is equal to 0. And let's get this in the form we like. Let's get this to have a coefficient of 1. So multiply the entire equation by 8/5. And we'd get x, double dot, second derivative, plus 40 times 8/5. 40 over 5 is 8. 8 times 8 is 64. So that gives us a characteristic equation of m squared plus 64 equals 0. And that means that m is equal to plus or minus 8i. I know I skipped a little algebra step. You can either plug it into the quadratic formula or subtract 64. M squared equals negative 64. When you take the square root of both sides, I comes out of it, of the radical, because it was a negative under the radical, and then radical 64 is just 8. So that tells us the general equation right now. It's x of t would be sine, well, let me write it down. X of t is c1 cosine 8t plus c2 cosine of 8t. I'm going to circle it even though that's not our final answer. Well, I mentioned this is an initial value problem, at least I think I mentioned that. The mass is released from rest at this point. So what are our initial values? At time 0, what is the position and what is the velocity? Well, at time 0, it's right here, so this is equal to 1/2. So at time 0, that's the position 1/2. This would be 0, -1/2, and so on. And the velocity, since it was released from rest, the velocity is 0. And these, I'm going to let you figure this out. I'll tell you what the C1 and C2 are. This and this imply C1 is equal to 1/2 and C2 is equal to 0. So the final solution, again, I didn't go through, I would have had to, in order to figure out what C1 and C2 are, I would have had to take the derivative of this and say that the derivative is equal to 0 at time 0. And that's what gave us C1 and C2. And so we really get x of t equal, C1 is 1/2, C2 is 0, so this here, I'll put stars around it. That's the solution. That's the position of the mass as a function of time. Now let's just do a quick sanity check. At time 0, what do we get? 1/2 cosine of 8 times 0. So cosine of 0 is 1. We get 1/2, and that's exactly what we, this is 1/2. This distance is 1/2 right here as well. So that position is 1/2. And then how do we find t and f? Well, we know omega. Omega is 8. We have the solution here. So t, the period is 2 pi over omega. 2 pi over omega is 2 pi over 8, which is pi over 4. T is pi over 4, so rather than write it in that corner, I'm going to put it over here. F is equal to 4 over pi. 4 over pi cycles per second. The period is that many seconds per cycle.